So welcome again, and thank you for joining us today on a live webinar on the topic of horticultural lighting, a growing opportunity, with a panelist discussion with some esteemed professionals in the economics and the science of horticultural lighting. Joining us today on the live webinar is Morgan Pattison, President of Lighting Scientists and Solid State Lighting, and Frank Sharp, Principal and Technical Leader of EPRI. For those who don't know EPRI is Electric Power Research Institute. As I mentioned before I begin, I'd like to go over a few housekeeping rules. First, keep your microphones on mute. Keep your video off throughout the presentation so we can focus on the speaker. If you have any questions, please do enter them in the chat box and we will do our best to answer as we go along or towards the end. We invite all IES members and non-members to attend to really spread the word of the Raleigh IES section, as well as new topics and relevant topics in illumination. At the conclusion of this program, folks will receive a little bit of a certificate from our organization to at least put in your CEUs for a half a credit. And following this presentation, this is going to be recorded. Well, this will be recorded and also placed on the IES YouTube channel so that you can review it later on. My name is Aparna Sprelik. I am the Education Committee Chairperson for the IES Raleigh section, and I am happy once again to introduce the topic for today. We will have a bit of levity. We will enjoy ourselves, and we should be able to learn a lot here today. Just to review the learning objectives, we will learn today a bit about horticultural lighting and what is the opportunity for horticultural lighting, what are the metrics and why are they important to horticultural lighting, and what are the typical performance level of horticultural lighting for installations that are already known. A bit about our speakers. We have Morgan Pattison, who's got a PhD in material science from UC Santa Barbara and research in GaN and micro activity for LEDs, and is advised everywhere regarding lighting. So we look forward to hearing from him. He will present first. And second, we will have Frank Sharp. He is the Principal Technical Leader at EPRI Knoxville facility and brings over 25 years of real-world experience in resolving unique technical issues regarding lighting and all kinds of areas. And you can read his full bio on our invitation. Now I'm going to turn the lectern over to Morgan so he can share his slides. So just a moment. Also, I wanted to mention that Lynn Davis will be the moderator for questions, and we will monitor your questions in the chat box. Here are our two speakers, just a nice look at them. And now I'll turn it over to Morgan.
All right, we'll jump right in. Thanks for having me. I always like talking about lighting, all different types of lighting. Horticultural lighting is something I've been spending a lot of time on recently because it is actually a growing application. And that's a lame pun, but it kind of goes with the territory with this topic. I work for Solid State Lighting Services. It's my own consulting business that consists of my wife and I, and we sometimes have some other folks that are around to help us out. We've been doing this since 2008, riding the wave of the LED revolution. My background is in LED technology, as Aparna said. That's a picture of me with my son and with Shuji Nakamura, my thesis advisor, who got the Nobel Prize for inventing the blue LED. That little guy, my son, is now 16 and helping me with the business and including horticultural lighting. So I've kind of gone full circle here, but in the business, in my background, you know, what I strive to do is understand the technical capabilities of LED and other optoelectronic technologies, and apply them to new applications, especially life science applications have been super interesting recently. Plants have huge commercial relevance, with horticultural lighting, and there's a revolution going on there, but there's also activity in animal responses to light and human health responses to light that I work on as well. To horticultural lighting, spent the last couple of years working with a company developing horticultural lights. Now I'm working on greenhouse lighting strategy for a client, and I think that gives me a good insight on this topic. Also was a member of the IES 45 Horticultural Lighting Committee, and just as an aside, I'm chair of the IES Outdoor Nighttime Environments Committee. So let's get going. This is horticultural lighting is a growing opportunity. There's a couple of pictures that show two settings, two applications. There's the greenhouse application where the light supplements natural daylight to extend the day length and control the day length, and to give that extra amount of light when the natural conditions maybe aren't quite doing it. And it's well known to increase yield and improve outcomes. The picture on the right is a newer setting, a newer situation. It's what we call indoor sole source, which is a euphemism for marijuana growth or cannabis growth. This is a really big deal. Uses a lot of light, and it's definitely an application that's taking off. The third type of horticultural lighting application, which I don't show a picture of, but actually Frank will have a bunch of pictures in his presentation, is vertical farms, which is similar to the picture on the right, just indoor sole source, but typically lower light levels and stacked trays, extending to pretty high heights. And that's kind of a typical breakdown of horticultural lighting applications, which all have somewhat different requirements in the practice. Here's an excerpt from a report I wrote, I co-authored for the Department of Energy, looking at the energy implications with horticultural lighting. And there's a couple of key points to take from this slide. First of all, vertical farming at the time of this report was, I think, 2019, had about 20 acres if you counted each shelf layer, the area of each shelf layer, 20 acres of growth going on. Supplemented greenhouses, something like 1,400 acres, and indoor cannabis growth, something like 800 acres. Just for context, all the vertical farming is pretty much leafy greens, some sort of lettuce. And, in field farming, there's something like 240,000 acres. So this is not big in the scale of agriculture, but it's definitely getting bigger. Now, with those areas and with an assumed power density, which is the next row down, the watts per square foot, you can do some math and then multiply that by, that would give you the total number of watts of light in these settings and across the country. And then you can multiply that by $1.50, which is a kind of a typical cost for a good quality horticultural lighting fixture, $1.50 a watt. And what you end up with is the indoor sole source lighting market is something like $2 billion worth of fixtures. Greenhouse is something like $600 million worth of fixtures, and vertical farming is something like $12 million of fixtures. Those are very loose numbers, but it gives you an idea of the scale of the applications. And just that these aren't small markets, these aren't small applications. And also, there's new, the areas are growing, and the power densities in each of these applications are actually going up. People are using more and more light in these applications. So horticultural lighting, uses the same light sources as indoor lighting, but it's characterized differently. And here's a little plot or a table from a Department of Energy R&D opportunities document that I co-author, which kind of gives you a map from general illumination metrics to horticultural lighting metrics. And so instead of lumens, horticultural lighting uses photosynthetic photon flux, which has units of micromoles per second. And so we can unpack that a little bit. Photosynthetic photons are photons between the wavelengths of 400 and 700 nanometers, which were, believed to have, or they enable the photosynthetic effect in plants. There's new research that says maybe that upper limit should be 750 nanometers, but that's not been baked into any kind of standard yet. Micromoles per sec, so you're counting photons, counting these photosynthetic photons, and you just use a micromole, or mole is something like 6.02 times 10 to the 23rd, and you use a micromole of those photons, and you call that 1. And you use per second to make the numbers work out. But anyways, so that's your ppf, or photosynthetic photon flux, which would be equivalent to your lumens. And then instead of lumens per watt, you have micromoles per second per watt. A watt second is a joule, so it simplifies down to micromoles per joule. And instead of illuminance, you have photosynthetic photon flux density, which is micromoles per second per meter squared. And this last line is just if you ever deal with luminous efficacy of radiation, which would be the maximum luminous efficacy you could have for a certain spectrum for a watt, for an optical watt. And that's just, sometimes we use that to figure out what the efficiency is, the radiative efficiency is of the source. So got the bullets there. What this leads to is a different design mindset. We want to optimize photosynthetic active radiation PAR instead of lumens, and that ultimately leads to the increased use of red LEDs. You have different desirable color qualities when it comes to horticulture. We're not trying to have high CRI or CCT or any kind of white. People do talk about the desirability of full spectrum for certain growth applications, but it's just different than what we need for humans. Now, that said, humans are walking around in these environments, so you can't completely ignore the human considerations. Another difference with horticultural lighting is that reliability expectations and demands are higher. In horticulture, we typically use Q90, which could be expressed as L90. It's equivalent to L70, except only a 10% degradation from the initial light output is accepted. So that's much more stringent than general illumination. That means, and the timeframes can still be 35 to 50,000 hours to reach Q90. And so that implies a lot of kind of different engineering priorities when it comes to these fixtures. Final point is, unlike general illumination, it is much easier to consider different form factors and different attachments because these are commercial kind of manufacturing products. So it's somewhat easier to optimize the fixture and the whole setting around the lights and the plants. It's just a little bit different. In addition to the photon flux density, PPFD, taken at one time plants, you also often measure the daily light integral, which is the number of photons that the plant receives in a day. And so you have to integrate the incident light over a day, which is not hard if you have a controlled indoor situation, but when you're in a greenhouse with variable natural light, it's something that's important to track. So here's a picture. This is the tool you need as a lighting professional in the horticultural setting. Instead of a illuminance meter, you need a PPFD or a PAR meter. This one's from Apogee Instruments. It's pretty well known. Lycor is another company that makes these type of meters. Let's see. So, as I said, there's increased use of red LEDs in horticulture, and the reason is watts or radiant efficiency of LEDs is on the upper left for different spectrum LEDs, different emission color LEDs, but you get more watts or more photons per watt based on physical constant Planck's law at longer wavelengths. So if you're just counting photons, you're not counting power or lumens, red LEDs end up being the most efficacious in terms of photons per second per watt or photons per joule. And red LEDs have gotten much better. They've been driven by the horticultural application. There's something like 70% efficient now. So you can use a lot of red in your spectrum. The plants like red, the plants respond to red, and it's very efficient, and that makes sense. So almost any horticultural lighting fixture will have either blue plus red or white plus red in the spectrum. In the lower left panel of this figure, you just have the human eye response curves. And then in the bottom right, you have various plant response curves, which kind of provide the connection between the spectrum of the provided light and the growth and morphological responses that the plant then undergoes. But ultimately, all photons are counted the same in terms of rating the efficacy of a light. This figure comes from a paper I co-authored in 2018. And I'll have all the references to these papers in my last slide here. So if we look at LEDs, you can see their radiant efficiency, their watts per watt, their radiant watts per, their optical watts out per electrical watts in the middle column. And then also their photons out per electrical watt in the right column. So as you see, red or deep red LEDs at 660 nanometers are very efficacious. Far red LEDs are also very efficacious, but they're outside of that photosynthetic photon window. They're 730 nanometers instead of 700. People still use them, but they don't count for your efficacy in the fixture if that's an important consideration. So as with any lighting, you have the efficacy of your LEDs, and then they get integrated into a fixture, and you have fixture losses. And the fixture can be tested, even if it's a horticultural fixture, it can be tested by a typical LM79 test methodology, and the results are converted into horticultural metrics instead of general illumination metrics. So it's the same testing. It's not expensive. It's the same cost. This is no longer a barrier to characterizing horticultural light fixtures. LM80 and TM24 are also used to figure out the depreciation lifetimes of the LEDs that are involved. So just as an example, a blue-red combination light, say 20% blue, 80% red. If you weight the photon efficacies, you'd end up with about 4.3 micromoles per joule. And if you assume the fixture has 20% fixture losses, you end up with about 3.5 micromoles per joule for the fixture. That would be a very good fixture. 3 micromoles per joule is also a good fixture, and 2.5 micromoles per joule is pretty typical. Here's some tables from RP45, IES RP45. It shows that the LED photosynthetic photon efficacy of fixtures can be 1.8 to 3.6. Good fixtures are getting up above 3 micromoles per joule. Personally, I wouldn't specify any fixture below that level because these fixtures are used a lot and the operating costs can be pretty high. So efficacy really does matter in this application. The previous incumbent technology, which is still quite prevalent, is high pressure sodium, particularly double-ended high pressure sodium lights, which show an efficacy of 1.9 to 2.1. That's the lamp efficacy. In a fixture, it's really closer to 1.7. So LED lights in horticulture have almost twice the efficacy, or are getting up to be about twice as efficacious, and they're on a lot. And so this is a big energy impact. And ultimately, I think they have better spectrum. That's somewhat debatable, but I've seen improvements to the spectrum. Also in the RP45 are some typical DLI ranges that you can design to. So if you have a target DLI, then that will then you can understand how long the lights need to be on for, and calculate out the photosynthetic photon flux density that needs to be designed to. And that's a really good starting point if you're doing this kind of work. So people make a big deal about spectrum with LED technology. I think sometimes it can be overclaimed, but that said, I have seen really clear impacts from having different spectrum. This is a study that was done in California with two different spectrum. There's an 80% red with 20% white, which is something like 7% blue and about 14% green, and then just a 90% red, 10% blue option. Those two options, the 80% red is on the left and the 90% red is in the middle, and then there's a metal halide on the right. And this information is on Lux's Instagram website. What we saw was much better root development with both of the LED options, and then healthy growth, but much different heights for the LED options, which the growers like to have that control. If they're going to start stacking the growth of these plants, they'd want shorter but still healthy plants. If they're not stacking, they like the taller plants. So spectrum really does have a morphological impact, but it's, like I said, sometimes it gets overclaimed. So that's pretty much it for me. Here's the documents I referred to. I've co-authored all of them. That makes it easy for me to just rely on my own memory and my own documents. And that's it. I'm be looking forward to your questions after we get through Frank's slides. Thanks very much.
Thank you, Morgan. Really appreciate it. Just a slight pause and we'll get Frank on right now. He's got his slides to share as well. Just a couple questions came out. Is there a red wavelength that is specifically best for plants, or is it plant family dependent? I don't know if you can answer that specifically, Morgan.
I think there's a best red wavelength. It's 660 nanometers because it's the most efficient, and the plant responses are marginal, but the efficiency is not. The improved efficiency is not.
Okay. Yeah, it's completely measurable. All right, Frank, proceed.
Everybody, for giving me an opportunity to present today. As our panel has already shared, I am Frank Sharp with EPRI, and I am based on the other side of the Appalachians from you all today over in Knoxville. But I supervise or lead all lighting research with EPRI along with my colleague Doug Lindsay. And we've been doing this lighting research at EPRI now for almost 20 years, and I've been leading it for about 12. So what we kind of want to talk today, as Morgan's already provided a wonderful background on kind of the basis of what we look at around CEA, or controlled environment agriculture, and the lighting associated with it, I want to speak a little bit about some of the drivers we've seen in the scope in space. So the real drivers we're seeing behind controlled environment agriculture, which is light-based or light-driven agriculture that is conducted indoors, is really the fact that we have a changing population. So be very upfront about this. Indoor agriculture is not competitive with traditional field ag. It is augmentative. And the reason that is so is it really focuses on short shelf life, high value crops. Morgan has a slightly more a broader ability to look. I do work for a federal 501c3, so I am not able to do cannabis research. I stop at hemp, but effectively we're all in the same space here. But most of my focus is around the production of healthy greens and fresh produce close to consumption. And it's because we're seeing more and more people coming onto the surface of the earth, and we're seeing an increase in urban populations. See, people are living in more cities. Farmland that is kind of para-urban or close to the urban environment is becoming less readily available. And we've already used a large percentage of our arable farmland. So just from a market perspective, some recent numbers from late 2022, indoor agriculture, or just the vertical farm market within the indoor ag, is predicted to be about $18 billion by 2028. And it was about, and it's increasing around 12% a year. And worldwide, it's going to be around $74 billion by 2027. But a lot of the things on the right, though, is what we're also trying to address, which is food desert. So almost any population or area in the U.S. at this point, and really throughout the world, that has a population density has some kind of food desert. And that's where there's not ready access to fresh produce within a mile or an accessible distance. And we also notice the bottom stat here is there's a lot of food waste. So by producing food closer to consumption, closer to the actual consumer and purchaser, we also get it to them fresher day of, day after, which gives them a longer shelf life, which also reduces the amount of waste. So for a real overview, what we're seeing is indoor agriculture is a growing load, all pun intended, as Morgan and I have both spoken about. This is a punny-rich space. But it's an expanding concept that uses a lot of different technologies. And I sit at the group at EPRI that researches all of those, HVAC, lighting, pumps, these kind of things. So I'm very fortunate that I kind of sit around a lot of subject matter experts that work in this area. But what we also see is that indoor ag is able to create local jobs, use existing infrastructure. So you think of that brownfield or empty building that's currently already got electrical service, utility service, it's just not used or it's underutilized. That can be revitalized. And again, since it is a controlled environment, there tends to be an increase in food safety. You have less risk of outside impacts on it. And you're not really driven by the fact of climate shifts or things, meaning that if you have a cold winter or a really hot summer, you're still producing crops because they're being produced indoors. And you have 365 perfect days of consumption per year, or production per year. And we see a lot of different cutting edge technologies being used to produce that. So a little bit of background on EPRI. I probably already shared this, but we are a 50-year-old 501c. We have about 1,250 employees worldwide in 30 countries, 450 member utilities at this time. And about 925 of us are subject matter experts, which means there's another 900 plus of people like Frank who focus on things like generation in all forms, nuclear, wind, gas, whatever, through transmission, distribution, impact, and also sustainability and environmental impact. And we even have experts in bees. So we have a very diverse range of research occurring at EPRI, and we're very excited to be partnering with our collaborators throughout the world. From an indoor ag side, we have been doing indoor ag research in an informal setting since 2012. We began formal research in 2013 when Doug Lindsay and myself began looking at lighting in the non-visible spectrum, including indoor ag. And we completed our first supplemental project in 2018, which we began in 2016. And since then, we've continued to expand. We have done numerous electrification events. Currently, we have, as of yesterday, 23 different containers throughout the U.S. collaborating with us. So we're getting a lot of different research from a lot of different climates on how these various systems work. So a little bit more background on how what we see. There is not a standard one way to conduct indoor agriculture. There's the greenhouse model, there's the vertical farm model, container models, and then there's kind of these hybrids that sit somewhere in between. But what we really see is that there's a lot of different forms being tried. And the last mile, the secret sauce, is how each farm really runs their lights, runs their other loads. But lighting is the predominant load, and the frequency they choose to use and the crop they particularly choose to grow are all things that really drive the selection and design of their farm. And so another key factor of this is, in most cases, these are soilless, hydroponic in some form, either float or little peat bogs or things like that. But also the reduction in water usage has been noticeable. We've seen over 90% in some cases. And again, I've already talked about that reduction of food miles, producing this food crop within 100, 200 miles of consumption. So if we're thinking in Raleigh, where, you don't have to be in the city, but you're kind of, 50, 60 miles outside, and you're feeding a range of cities around it. If you're in Knoxville, Tennessee, where I am, you would probably position a farm maybe somewhere between Knoxville and Nashville, or maybe even in Chattanooga, Tennessee, and you could go to Atlanta, Knoxville, Nashville, Chattanooga, and even Asheville, all within the same day. And so that's what we're beginning to see, is the strategic locations of farms where they are close to larger urban populations, but they are typically, and we're finding them in kind of that border space. And I mention that because very recently, a 90,000 square foot vertical farm opened in Danville, Virginia, just a little north of you all. And that farm is currently, to my knowledge, the largest vertical farm in North America. And it has a sister farm that's about 75,000 square feet. That's right outside New York City, in a former steel mill. So we're seeing a lot of different concepts being tried. So what we really want to talk about, though, is the amount of energy. And the reason that's important is because lighting is about 60% of the energy load typically. And these lights are used almost every day. In the case of a greenhouse, they're used to augment. So if you're having a very solar-rich day, you may turn them off or down, only use them in the shoulder hours. But in the case of sole sources, Morgan pointed out that we also have the vertical farm and the container farm, where those lights are providing all the light that's in the farm. And this is an application where efficiency is discussed, but it's the secondary question. It's production that's the driver. And so you want to have the most efficacious lights you can to affordably produce the crop you want at the rate you want to produce it. And so what we're seeing, though, is some of these larger warehouse farms are the equivalent to a steel mill, 40, 50 megawatts in some cases. And we're seeing greenhouses, which are a little more seasonal. They're on not as much in the summer, but more in the fall and spring and winter. These are also noticeable loads. And a farm I visited a few years ago was a 45-acre greenhouse. It was a 25 megawatt load. What was ironic is they had plans to build out to be approximately 180 acres when they were fully built out. They have not completed that build out yet, of course. And they were going to be about 100 megawatts, which was interesting because there was a 100 megawatt steel mill on the other side of the street. So we're seeing a lot of energy being used by these farms, and that is being driven by lighting load. I've already shared a lot of this before, and as I've been saying, and others say, lumens are for humans, and what we talk about here is PAR, DLI, PPFD, which has arguably been covered today. But those are the things that really drive production and really drive these farms forward. And the data they collect on their production, their energy use, their light use, these kind of things, is really what makes the farm change and evolve and become the type of farm it wants to do. And you can also see there's some other loads, maybe not relevant to the people on the call today. But if you have, or you're working with mechanicals or you're partnering with other trades, these are definitely important areas. Dehumidification is an expanding area within indoor ag that is becoming more and more relevant by the day. Greenhouses typically have been high pressure sodium dominant. This is a technology that's been around for a while. The greenhouse model that's used historically in the US is the Dutch model, which has been working itself out now since really right after World War II. And so there's a little bit of concern about change. They have something that works and they know it produces, so they are a little more resistant. But we're beginning to make some inroads when we talk about LEDs and some other things. And one of the real advantages of LEDs is you see these lights here are, This is a greenhouse. It's about, I think, 45 acres at the top. 45 feet at the top. But the lights themselves are, 10, 12 feet above the canopy. With LEDs, you can get much closer. So you can deliver that light much closer to the crop, which actually in many cases, not always, but in many cases can help accelerate the production of crops. So this is an area where there's a lot of discussion about transitioning either old farms or farms that are in the process of being built to either a blended LED, high pressure sodium, or all LED. Vertical farms are almost exclusively LED, and many times they actually have custom LEDs for that farm. They've gone to a manufacturer. And all of these LED fixtures in ag, they use the best quality product. They need that high quality light. They need that longer lifespan, and they need a high quality light that's not going to shift and decline. So they tend to underdrive and overbuild. And that allows them to have a long life that is extremely productive when it comes from plant science's perspective. But in this case, this particular farm is using a full spectrum white. They do have a boosted red LED, which is not visible in there, but if you put it under the par meter or even the spectrum analyzer, you'll see it pretty obviously. Here's a container farm model. Again, we have 20 plus of these in the field at the moment. This particular model tends to use a red and blue blend. I tend to call it purple, but it is really a blue LED with a red boost. And the discussion here is the fact that the plants don't use green, and so and some other spectrum. So why deliver it? Only deliver the spectrum that is needed to grow the crops. There is some debate within indoor ag, which is the better path. I think at the moment, full spectrum white with boosted red, boosted blues are really going to probably take over in most form factors other than container farms. But in container farms, there's still a lot of discussion around the use of red and blue standalones with some kind of controlled blend. So I want to kind of complete today and kind of talk about some specific fixtures we've had in our lab, and we've run through our testing and our measurements. So again, we've already kind of talked about the various forms of agricultural LEDs. They're full spectrum white without boost. These are not really the most productive, but they try to simulate the sun, but they don't really have the full sun spectrum. So the next step really is when you get to the full spectrum with a red boost, and that's what we're seeing a lot of greenhouse and vertical farms moving toward. The blended red and blue I've shown, and then there's also kind of a model with a blended red and blue with a boosted nanometer of a specific type to kind of drive a particular taste or particular crop. We're seeing more and more of that occurring though in academia. These are not necessarily fixtures that we're finding in the mass consumption or mass sales. But vertical farms are really focusing on using customized or highly specialized commercial fixtures. Greenhouses typically have thousands of fixtures. These are very large applications with thousands of them. And then even in a container farm, 320 square feet, so 8 by 40, there's 3,000 watts of LEDs in those. So it's a very dense environment, and kind of, as I alluded to on a previous screen, a container farm is equal to 4 to 5 average U.S. homes in daily energy consumption. So very interesting. So here's a couple of fixtures that we've done some testing on. I included lumens in these, even though they're not really relevant for this discussion, but I did want to kind of share, that basically this is a 600 watt LED fixture producing 106,000 lumens. And it's but the key thing to look at is that PPF, that micromoles per second that's being delivered. So this is a 1,500 micromoles per second, very high radiant flux. This is a really well-designed fixture that basically builds the LED into the white and a normal full spectrum white. So the red boost is built into the fixture. This one's a little more visible on how they do it, but they use a standard white, then they add a red boost. But again, the key things here about a 650 watt fixture, roughly with 127,000 lumens. But when we look at the PPF, this is over 2,000. Really high output, and I should add, these are measured in the same way that I already talked about with kind of a par meter. But we tend to use a slightly different brand, but there's several quality products out there. Ours happens to be a gel optic but we have the apogee meter and we have some others. So lots of good tools out there if you're beginning to move into this space. This is a slightly modified version of the previous fixture. It's a little bit bigger, produces more lumens, but it's a different form factor. You'll notice that this is a little more linear where they can hang it, where this one's got more of a finger design where they can position it differently over a particular crop they're targeting here. And then here is a fixture that uses a white spectrum. It has a red boost. So if you saw this fixture in my lab, sorry, it doesn't appear as red as it looks in the photo until you look at the surface. If you look directly at it, which is somewhat difficult because it is very bright, it appears white or kind of slightly pinkish, almost like an aged lamp that we would have seen historically. But in this case, when you really look at the light, it's got a really noticeable red. But what I want to show here is this is a controllable fixture. So this is a fixture that you would think about adjusting the output based on the amount of sun maybe you're getting in your greenhouse every day and adjusting its amount of output. So most of these fixtures operate, have some kind of 0 to 10 volt driver. But again, they're not going to be dimmed or controlled based solely on a schedule. It's going to really be based on the light level at the time or particular crop size or whatever is going on underneath it. And the last fixture I'll talk about today is a little bit different look, but it uses kind of again, a full spectrum white with a red boost, but it's actually a very light, thin fixture that uses a finger model. So it allows you to do a lot of things with how you orientate it, but it is also a lower wattage fixture. This is only about 170 watt. So this is designed for a much smaller farm where you're growing a crop maybe on a smaller scale or something where you're not exactly building out for commercial. So this is maybe a high-end residential or small commercial application. So with that, I will pause and take questions or whatever. Thank you much.
Thank you, Frank. Appreciate that overview. At this moment, Lynn will be taking over on the questions and answers or questioning period. Lynn, you want to go ahead and unmute?
Sure. So I've also unmuted everybody. So while you're thinking about questions, I've got a couple that that come to mind. The first one is for Frank. So Frank, when you're applying these horticultural lighting recipes, is it something that's applied 24/7, or do you have like some sort of duty cycle where you turn the lights on for an X amount of time and then turn them off?
Well, yeah, most of the time what we're seeing is these, we'll kind of focus on something that's solely provided by electric light. Clearly, if we're in a greenhouse or sun modified or sun augmented, that's a slightly different when you use your lights. But if we're in a space where we're only using electric lighting, we typically see these lights running somewhere between 16 and 18 hours a day, but you can program them or schedule them. The plant itself doesn't really care if it's 6 a.m. or 6 p.m. if you're providing all of its light. So because of that, what we have seen, some utilities who are my most common collaborators is really work with farms to maybe provide them an improved power rate. Sorry about that, my lights in my office just went off. But an improved power rate or a beneficial power rate to operate during non-peak hours. So that's something that's a great question, Lynn, and something that a lot of utilities are looking at. I should have added, because both what Morgan and I have talked about today, that you're not measuring these fixtures with the standard lumens per watt. Sometimes these fixtures are, in many cases, most cases now, these fixtures have not fit into traditional utility rebating programs. So many times you have to either get a special rebate or you have to go talk to a utility where they can include a measurement of, PPFD within their lighting rebating program to make sure these LED fixtures are compatible with their rebating programs, which allows them to become more accessible to the farmer.
Okay, thank you. So I've got a question.
Let me
Yes,
just add
Morgan.
to that, the photo period can influence flowering, right? So there's that element as well that needs to be managed. So with lettuce or leafy greens, it's only ever in the vegetative state. It's just adding mass. But with any kind of fruit crop or flowering crop, you can trigger flowering by engineering the photo period. And so that's, if you're in a greenhouse, you kind of working with or against natural daylight patterns, but indoors you have full control over that. And so that's a pretty interesting difference, because like Frank was saying, in a vertical farm, some vertical farms even run 24 hours because the plants never need that signal. So there's some differences depending on crop types when it comes to the photo period.
Okay, thank you.
Could somebody address remote drivers for LEDs and the pros and cons of getting them out of the grow space?
Maybe Morgan, you want to try that?
Yeah, Frank might be better. I mean, I've heard that proposed, but it's
Yeah.
I'll let Frank go first. I've thought about it, but I think it's more of a utility kind of question.
Yeah, and it kind of is. The durability perspective, if the fixtures are all pretty high quality, so they're probably going to operate equally well whether the driver is within the grow space or out. But from a temperature perspective, the LED driver, is producing some heat. The LEDs themselves, of course, are producing heat. So by moving the driver outside, especially in a greenhouse or vertical farm where maybe the conditioned space is not all the way to the ceiling, you're improving the likelihood of that driver living its extended lifespan or living its full lifespan, because you're not keeping it in a hot, wet space. But just from a utility energy perspective, it doesn't matter. It's just more of the durability. And we have tested LED drivers, both remote ballasted or remote driver, I guess would be a better example there, or the better term, and also on lock fixture drivers, and we've seen similar lifespan, slightly different thermals, and we do have some thermal cameras we use for that. So it is a great question. I think one that we're still looking into.
I think remote power supply, remote driver has the potential to be better, but I don't think the benefits have really been convincingly demonstrated. So that's kind of where I'm at. Like a good horticultural fixture isn't that expensive, and the driver just depends on the manufacturing quality. It can be very good and live a long time, and super efficient. So it's like, what ends up being the benefit in that situation?
Here's a question that came in from Christine on the chat. So some manufacturers are saying that growers cannot currently afford the expenditure on LED lighting because rising energy prices are constraining their budgets. Is that, you feel like that's a real issue? And if so, how can we overcome this?
I'll give my 2 cents first. If energy costs are becoming an issue, you can't not afford LED prices. The primary cost is operating cost of the electricity going into the lights, not the lights themselves. And it ends up being much more expensive operating cost wise compared to the fixture cost. What I think is happening is, vertical farming is, and all of this farming, it is governed by a fundamental limitation of the plant process to convert photons to biomass. And that's a fundamental process. And, you want to get your LEDs as sufficient as possible within that process. But for many crops, the cost of the light's going to cost more than the crops themselves. The crop, and I do have a slide about this, but I didn't show it. It's at the end. The crops where it makes sense are high value crops like leafy greens, where the light ends up being a small fraction of the ultimate cost of the crop. So that's why those crops are commercial, but they're still very sensitive to electricity costs, because lighting and electricity costs are a huge portion of the total cost in the greenhouse or the vertical farm, and they're very close. I think if anyone's followed this space, there are a lot of vertical farms who've kind of come and gone because it's a very close case economically, and LEDs are almost as good as they're going to get. They can get slightly better, but that's not going to change the basic economics anymore. So yeah, there have to be other clever ways to reduce costs, but we're getting close to the limits of productivity.
Okay, thank you. Frank, anything to add?
Yeah, I mean, I think we're pretty much on the same page here. I mean, I would add that we are a little bit more technology agnostic, but I kind of agree with Morgan that LED is where it's going to be moving, but the transition may take a while. When you have a greenhouse that has been built with high pressure sodium, they are going to be hesitant to convert that entire space in a razor thin margin business to LED. So you almost have to wait until they go through a full cycle of their product or their lamp technology. But yeah, LED agricultural lighting has gotten much better. And I think much like, say, roadway lighting, an area that I've spent a lot of other time in, we're going to continue to see a decline in prices. The number of units get manufactured increases, but there is a top limit here. These are never going to be as common as, say, a commercial trough or something like that. And because of that, the operational costs for these farms, I mean, we all kind of have followed this industry. It's still a very high risk, entrepreneurial driven space, and there is a lot of failures. And a lot of that is typically the farm has not thought itself through all its operating costs when it's built, or they haven't maximized it. And the use of LEDs can help them increase the productivity of their farm without negatively increasing the amount of energy they use. It's a push to slightly improve. Again, things we've kind of talked about is, you know, we see 1,500, 2,000 watt high pressure sodium going down. That's not being replaced by a 500 watt LED. It's being replaced by 3 600 watt LEDs or 4. You know, so the energy is about a push, but the fact that you can get those fixtures closer to the crop and make the production go faster is where we're really seeing the benefit of the LED.
Okay.
More crop, more profit, more value, basically.
Makes perfect sense. A question came in from May over the chat, and she's asking, in high sun areas like in the south, in augmented greenhouses, is there an advantage of LEDs over high pressure sodium? I guess this was an issue in the early years of LED horticultural lighting, and she was wondering if it still was an issue.
In the south, there could be an advantage just because of the less heat generation from the LEDs, which people perceive as a benefit in the north. But definitely, if you're in a high DLI area like the south, lower latitudes, you know, shading becomes more of an issue and electric lighting becomes less of an issue. It's just on less. So that does affect the economics.
Yeah, absolutely. And I've mentioned in my slide the same kind of thing, that, you know, you're in a greenhouse, your lights are on during shoulder hours and shoulder weeks or days. You know, so if you're in a hot sun area, your lights are on less, period. And if you're in an area where there's more rain, your lights are on more overcast. So it is a bit, we've kind of addressed those questions as it's more situational and geographically driven, or so, yeah.
I have a final question. Really, we're coming up to the hour. Is vertical farming and artificial light farming considered more organic and pesticide free? Because that could be the push for this to, you know, kind of grow in the industry. You know, pesticide free product.
I don't know about the organics. Oh, Frank, you go ahead. Sorry, I've been going.
No, go on, Morgan. I will follow you on this. Go on.
All right. I don't know about the actual organic certification. There's definitely the potential to use far less pesticides and water indoors. And that's a good thing. And to use less land per output, per crop. The flip side is that this is an energy intensive operation. You just use more electricity than outdoor crops, and ultimately that means that the greenhouse gas impacts are going to be more until we're in a more renewable energy situation. And it, you know, it doesn't matter how far you're driving the crops, that doesn't counterbalance that fact. So this is it's not really a sustainability play in terms of energy. It's a diversification play, and it's like Frank said, it's a complementary application or part to the food supply chain. And so that's Yeah, that's how you got to look at it. But yeah, pesticides would definitely be reduced.
So it could be organic. It could be considered
Yeah.
organic.
Yeah.
Well, yeah, and I have spent a little bit of time directly on that. We've only found one farm that has gone for organic certification, and it's because of cost. So most of the time it's being sold as farm to table, locally grown, not organic. So even though it could potentially qualify as organic, the cost of certification has been a bit of a wall or a burden there. The pesticides, herbicide reduction is very noticeable. Water, we've already kind of talked about. I will kind of follow up on the sustainability question. We're kind of doing that math. What we're looking at is the different parts of the country has different generation profiles. So if you're coal rich versus gas versus solar and wind, those sustainability questions are slightly different. Everybody on this call in Tennessee and North Carolina, lettuces, fresh greens are traveling 3,000 plus miles. If you're using field production, that's diesel driven, and in the car, in the farm, harvest produce and shipment. What we're trying to look at is if you're producing it using greener energy, closer to consumption, maybe even delivering with some kind of green delivery system, an EV vehicle that's being charged by wind or solar, we could maybe shift some sustainability. So, but I think more dead on today, the discussion at the very best, it's a push, and we're trying to see if the next step for this would be an improvement. Yeah.
I think there was one last question that came along in the chat box. I don't know if you can read it fully. Lynn, can you see it fully? It's sort of hidden in mine.
Yeah. Are there any drawbacks to artificial light grown crops, similar to possible side effects from genetically modified organisms?
Everything that we've seen, everybody uses the same seed. They're not using GMO seed. So from my perspective, the answer is it's the same, if not better, because you're growing it indoor close to consumption. Morgan, what are your thoughts?
Yeah, I agree. I think it's light's light, photons are photons. We can do some engineering and control to engage different responses by the plant, but these aren't just responses that wouldn't occur in nature. They would also occur in nature. We're just being a little more fine-tuned. So I don't think there's any risk of what they're asking.
Harm.
Yeah.
Well, excellent. Well, thank you both for presenting to us and giving us a new way, shedding new light on this growing agricultural lighting and horticultural lighting. Any final comments from you, Lynn, before we close it out here? We're right at the hour.
No, that's fine. I appreciate both of you. Great presentations. Learned a lot, and I'm sure our memberships did as well.
Absolutely. And thank you so much. And the membership here, if you ever feel like reaching out, you can certainly contact Morgan and Frank directly as well.
Definitely. Thanks.
Yep. Thank you
all.
all.
Have a good afternoon. Great weekend. Thanks all.
Bye-bye.
All right.
Bye.
Bye.